Well, our last meeting we were discussing, we discussed the question of converting percentages of alcohol to different bases. And in order to illustrate that, I handed out a little problem set, which I asked you to try to work out for this morning, the answers to problem 1, which had 5 or 6 parts to it, 6 parts. And those seem to be rather straightforward. The intention was to use the little leaflet with the conversion tables, but to carry out the interpolations so as to get the answer precisely to the nearest hundredth of a unit. Anyone have any questions they want to ask about the technique of using conversions as we've outlined it so far?
We have a quiz or test on this, but we have all the most of the factors and the tables available. I know we'll have the tables, but will we have the factors too, like for density conversions?
Well, I haven't thought about it yet. In the past, I've given the students the option of whether they want to have an open book exam, as all your notes, books, or a closed book. Invariably, they choose open book, which means you get more difficult problems, but you have materials to work with. So when the time comes, I'll ask you that question. Of course, if anything, any kind of a problem where you would expect it to be used tables, well, naturally you'd be expected to be able to have them. All right. So we'll come to that when the time comes. Well, what answer did you get for problem 1? Let's see, the question was converting 95.57% by weight to volume percent, and to percent of proof, I guess it was. So who got the answer to that? 97.17. Right. 97.17. Or the percent of proof, of course, then would be exactly 2 times that, or 194.34% of proof. I would like to point out that this happens to be the exact percentage of alcohol in what we call the azeotropic mixture, or the constant boiling mixture of alcohol and water at 1 atmosphere pressure, which means, as we'll see later more clearly, that this is the maximum proof that one can obtain by distillation techniques using 1 atmosphere pressure for the distilling system. So about 194 proof is the top you can get. Now in practice, about 193 is about as high as it's ever gotten, but if you had a sufficient number of stages or plates or in a column, sufficient number of stages of redistillation, multi-stages, you could approach 194.34 as the upper limit of the strength of the distillate. In practice, of course, industrial alcohol is usually sold at 190 proof. It probably was distilled at some value up around 193, and the units are capable of producing very neutral alcohol. They're talking about industrial alcohol now. But in practice, it's reduced down to 95% by volume, or 190 proof. As we'll see later, this constant boiling mixture, or the azeotropic mixture of 194.34 proof, has a boiling point at 1 atmosphere of 78.15 degrees centigrade, or 172.7 degrees Fahrenheit. What answer did you get for part B, which was to convert the same percentage to mole percent? 89.40. 89.403, but you drop off the 300 to make it 89.40 to answer the question. Ask for it to the nearest hundredth of a unit. So again, 89.4, not quite 90%, is the composition on the mole basis of the azeotropic mixture. Now, part C was asked to convert 12.50% alcohol by volume to mole percent. So how do you proceed to do that, utilizing the tables? How'd you do it?
I took the volume percent and converted it to weight percent using the tables, and from the weight percent I found the mole percentage.
That's right. What answer did you get?
4.20.
4.20, that's correct. I thought I might just go through the solution to that one to show you how I set up the interpolations. It's a rather simple, straightforward thing, but when you're converting in table 2 from volume percent to weight percent, well, you have to you really have to write it out on a piece of scratch paper or something in order to make sure you get the fractional part there. So in other words, the way this would be part C. The way the question is 12.50% by volume to mole percent. So the first step then is what I do, I write down 12 point out of the table, looking at the table, to the one that's closest to the values that are closest to 12.50%. The one that you can read directly is 12.515 volume percent equals 10.1 weight percent. Then reading one step over in the table, you get 12.393% by volume is equal to 10.0 weight percent. And so the difference here, 0.12% by volume, is equal to a difference of 0.110% by weight. And so then 12.50 volume percent is equal to 10.00 weight percent plus, now the difference between 12.500 and 393 is 0.107. 107. The difference between the value we want And but this is a so then that fraction of this difference, 0.122, which is equivalent to a tenth here, so that's times a tenth. So that gives you then, multiplying this out, this is 10.00 plus the value of this fraction here is, it comes out to be 0.087, or in other words, the answer is 10.087 or 10.09 to the nearest value, weight percent. And of course, the interpolation is easier than going the other way from weight percent to either volume percent or to mole percent, because it's essentially the same procedure. So now we have 10.1 weight percent is equal to 4.209 mole percent. This is table 1 of the tables. And 10.0 weight percent is equal to 4.164 mole percent. And a difference of 1/10 here on a weight percent basis is equal to a difference of 0.045 on a mole percent basis. And so for 10.09% by weight would be equal to this figure here plus the fraction, plus whatever fraction the difference is here, is equal to 10.00 plus wait a minute, is equal, wait, wrote down the wrong thing. Is equal to 4.164 plus whatever the fractional difference is here, which is 0.09 times 0.045. In other words, 1/10 unit of weight percent gives this interval or difference on a mole percent basis, and we have this much of a weight percent basis, so it's 900 times that, or you can do this over that. So it'd be 4.164 plus this fraction comes out to be 0.039. So the answer would be 4.203 or 4.20 mole percent to the nearest hundredth, as the question was asked for. So generally speaking, then you write down the two values here out of the table and get the difference here, so as to be able to get the fractional interval for the interpolation. Well, let's see. Then the other questions about this. How about problem D? That's very straightforward, using a formula in the handout tables. The question was to calculate what is a gram per 100 milliliters at 15.56 degrees if the volume percent is 80.0. So there's a formula in the book that just multiply 80 times 0.79313. It comes out to be 63.45 grams per 100 milliliters. Grams of alcohol per 100 milliliters. Of course, at 15.56 degrees centigrade or 60 degrees Fahrenheit. Part E is just sort of the reverse of that. You can either use Formula 3 or Formula 4. And what answer did you get for that? The answer to Part E. Who's got the answer? You got it?
75.6% volume by volume, 151.2% proof.
75.65% alcohol by volume, or 151.30% of proof.
Probably rounded off.
Pardon?
Probably rounded off that, the reciprocal figure before I multiplied.
Mm-hmm. All right, the last one of those had to do with converting a solution which is said to be 30 degrees overproof in the British system to mole percent. This is a little more involved. And based on the information I've given you, both in that handout table or here in the lecture, there's a little bit of uncertainty about the exact value of British proof. But anyway, I used the fact that as I gave you in a lecture last time, that British proof is stated to be 49.276% alcohol by weight. And of course that's a non-controversial value. It's independent of temperature. And so if that's the value, then as I indicated before, using the relationship given in our table 2 here, this would be equivalent to 57.09% alcohol by volume in the U.S. I think generally speaking 57.1 is considered to be the equivalent percent alcohol by volume for British proof. But it would be 57.09 according to my calculations.
What's the answer to that?
Pardon?
Is that the answer?
No, that's not the answer. That's just a conversion factor to use. That's what you start with. Well, perhaps I'll write out the solution to that, since it's slightly obscure based on the information you had. Well, this is part F. An average 30.0 overproof, as they frequently abbreviate it, of course, is equal to 100 plus 30, or 130% of proof in the British system. Now, the statement in our official tables, as I referred to, excise and custom tables, says that proof, British, is equal to 49.276% by weight. And then I'm by the technique of conversion, extrapolating, I find that 49.276% by weight is equal to 57.09% by volume. This is the U.S. system. U.S. based on U.S. density tables. It's very likely that the tables that they use for densities differ slightly, so that to be just in the British system, so that to be a slight difference in this. So in other words then, so then the percent by volume using our US system would be equal to 0.5709 or 571, whichever you want to use it, times 100 plus 30, which comes out to be 74.23% by volume. And so then converting that 74.23% by volume percent, and interpolating again, it comes out to be 67.02% by weight. And so we were asked to get mole percent, so simply using the table 1 to convert that to mole percent, and then the conversion 67.02% by weight. Interpolating to the nearest hundreds comes out to be 44.28 mole percent. That'd be the answer. Yes?
Use that, the 57.09 as opposed to the 57.15 that you have in your brochure? Or just make it
Yes, I mean, I would suggest that you correct that, and yeah.
You correct .5715 to .5703.
Oh, I said, well, there's one way as I indicated last time, it comes out to be 5703, but I think this is a more fundamental, so it comes out to be 5709. So don't worry about it. The little small differences here of these various ways of converting, but so you use either 57.1 or 5709. I think that's the best figure that as in my opinion now, is for converting. Mm-hmm. Well, when you hand in written work, why I would hope you do it neatly, and so it's easy to read, easy for me to see. Not use a lot of don't put down on your hand-in work. If you do longhand multiplication, for example, don't show me all that. I just want to know what's multiplied by what and the answer. But a proper solution to these questions here would show something like I did here, how you got the fractional interpolation, so you got the value out to the axis I asked for. Well, unless there's some questions on this aspect of it, I would make some comments about the approach you would use to solve problem 2 of this set. Which again is partly and mostly an exercise in converting units, but it also involves a very simple application of what I'd indicated before of solving a problem by writing a mass balance, material balance. So this particular problem states that the feed rate, the feed, that is wine, to a continuous distilling unit is 7,500 gallons per hour, and it contains 10.31 volume percent alcohol. That's all you need to know to work subparts A and B. The specific gravity value is required in order to work part C. So how would you approach that? Well, as I say, A and B is really just a continuation of the techniques you used for problem 1 make the conversion. So the first step would be convert 10.31 volume percent to weight percent to mole percent, and then what is mole fraction? Merely mole percent divided by 100, or in other words, a fraction of the total that's alcohol. Is there any question about that? I'm not going to work it for you, unless you, but of course you can do that very easily, I would think. Part B asks for how many pound moles of feed per hour. Now, how would you go about that? In other words, pound moles means what? It's a method of measuring the amount of a material, just like gallons would be, or the volume would be, and just as pounds would be. If we consider the feed as composed of just ethyl alcohol and water, that is neglecting the other materials, the dissolved solids. Why, the total number of pound moles per hour of feed would be the sum of the pound moles of alcohol, or in other words, the pounds of alcohol divided by its molecular weight, plus the pounds of water divided by the molecular weight of water, and the sum of the two. That would be the pound moles of feed. In which case, you could do it without any tables. Multiply. Find what the weight percent alcohol in the feed is, and multiply them. Well, I guess you have to use you have to use the rate here, 7,500 gallons per hour, and convert that to pounds of feed, and then if you know the percentage of alcohol in that on a weight basis, then you get the pounds of alcohol, and then you divide the pounds of alcohol by the molecular weight of alcohol, and you have the pound moles. And the difference between the total pounds in the feed and the wine, less the amount of alcohol would give the amount of water, again neglecting the extract content, and that divided by 18.02 would be the pound moles of water, and the sum of them would be total pound moles of feed. However, there's a slightly shorter way of doing that based on the tables that I handed out, and that is to convert the feed rate, which is given in gallons per hour, to total pounds per hour. Then using table 4, that little leaflet, you can find what the average molecular weight is for whatever the weight percentage of alcohol in the feed turned out to be, and doing an interpolation in table 4 to get the average molecular weight, you can divide the pounds of feed per hour divided by the average molecular weight, and you get pound moles of feed per hour. So you can do it either way. Or you can do it both ways, check your answer. Might be, if you don't have anything else to do, that might be good exercise. As a matter of fact, many times solving problems, if you have an alternate way of doing it, it's a very good way to use both methods just as a check. If they don't agree, you made some error in one of the solutions. Or possibly you used, in one solution you used a little bit the wrong basis for some reason or other. Now, if you have the answer to part B, well then it's fairly straightforward to work part C by writing material balance with respect to alcohol and solving for the unknown. So I'll just indicate that we had. I won't put the answers in here, but I'll just show what the what you need to do. First of all, as I'll elaborate on more later, most of the types of problems that we have that involve some aspect of process, such as a distillation process, one of the first things one should do is draw a diagram, a little simple sketch showing the flow pattern or the flow diagram so that you can visualize what it is about. Well, in this case, we have a very simple thing. We just indicate the distilling column here in which we put a feed, or the wine, into some middle portion of the column, and this is, and it's very good practice when you're writing a solution to write the explicit data down, that is the data that's been given, 7,500 gallons per hour, and 10.31% by volume. And this is separated into a bottoms product, or just or bottoms as we usually call it, and a top product. And we'll just indicate here that this is the product of the distillate. And what did it say? Let's see what it said. Distillate is 168 proof. And represents a recovery of 98% of the alcohol. So, I may be getting a little ahead of myself here, but I might say in the way of symbols that we use throughout here, that as I've already said, that feed, we generally use the word F, and bottoms, B, and depends on what's a little bit here. Generally a product is the main product. I use the word P, or whatever it may be. Or steam sometimes, we use the term S. If steam enters a product directly, in direct injection, for example, and so forth. Then we use the letter X to represent the mole fraction of a volatile component such as ethyl alcohol in liquid streams. In this case, of course, that's the only thing we're considering is liquid streams. And so then we write a subscript to indicate which stream we're talking about. So X sub F, for example, would be the mole fraction of alcohol in the feed stream. And similarly, X sub B would, this may not be very clear the way I'm writing it. This written, if you're doing this on a typewriter, that'd be a small x, the subscript capital F, or X sub B would be, of course, mole fraction of that in the bottoms, and so forth. So in other words, in this particular problem, the only equation that we need to write then for this is that for an alcohol balance on a mole basis, we have feed in gives the feed in times the percent of alcohol. I might as well write out the symbols. The feed rate times the composition X sub F would represent the amount of the alcohol going in, and that has to equal to the alcohol going out. And in this case, we don't know anything about the bottom product. Nothing was stated about it, but we do know that 98% of this alcohol was recovered in the distillate, so we can write 98%. Wait a minute. 98% of that is recovered in the product, and that's you can use a symbol P times X sub P. And so we know that if we've made the proper conversions, we know this, or we can make the proper conversion to get this. And this 168 proof has to be converted to that, to the proper mole percentage, so then all you have to do is solve for P. And that'd be the answer. I mean, solving that for P. So P is equal to F times X sub F times 98 divided by X sub P. Part D of that asks for how many wine gallons and proof gallons of product at 168 proof. Well, that's very straightforward. The easiest way to do that is find out how many wine gallons and just use the volume percent basis. Well, let me go back. There's another point about this one here. The how would you convert 7,500 gallons per hour to pounds per hour with the information you've been given in the problem? I mean, that was necessary to solve part B. Part B, and then you use it again in part C. Well, this requires a knowledge of of a conversion factor that you may already know, but I haven't given to you before. And the basis is that, well, 1 gallon of water at 60 degrees Fahrenheit weighs 8.34 pounds mass. Some people frequently use 8.33, and that's a closer figure if you're talking about room temperature, 68 Fahrenheit or 20 degrees centigrade. But and of course, in a problem like this, we didn't give you the exact. We didn't tell you what temperature this was measured at, so you can use. You can assume it's 60 degrees Fahrenheit. But in practice, of course, that'd be a little cold for plant process conditions. But as I said once before, when you're working problems, if there's some bit of information that's omitted or not available to make a completely rigorous solution, well, you just make a reasonable assumption. And for example, you make a reasonable assumption of some temperature that this feed here, and the easiest one to take is 60 degrees Fahrenheit, because that's the basis of our measurement of volume percent alcohol. But it wouldn't have to be that. It could have been measured at 20 degrees or 30 degrees centigrade or 68 or so forth. But anyway, for practical purposes, it doesn't make much difference whether you use 833 or 834. But this is the correct value of 60 degrees Fahrenheit. So in other words, we need to find out how many pounds per gallon of there are in this feed material. So how do you do that? Well, the density of a solution in terms of, in the English engineering system, is equal to the density of water times the specific gravity. So using the engineering units, we'd have the density of the feed, or that wine material, is equal to density of water, which is 8.34 pounds per gallon, times the specific gravity, which means the ratio between the weight of a given volume water and the other way around, the ratio between the given volume of the solution divided by the same volume of water. Well, I could write this out. Okay, this is pounds mass for water divided by the specific, or times the specific gravity, which is the pounds of solution per unit volume or per gallon, divided by the pounds of water per gallon, and that's what this is. So that would cancel out. So in other words, this is the specific gravity. So in other words, you simply multiply 8.34 pounds per gallon times the specific gravity, which was given to you as 0.986. 0.986. So that would be the pounds per gallon of the wine. Pounds of feed per gallon. Now I think I've given you all that you need to work the problem. In the next or one of the other subsequent meeting, I will have a little bit more to say about the technique of conversion of units in general, and tell you where you can find the basic conversion units and figure out your own from those. Well, any questions about these problems? So mostly just a little exercise and applying common sense and using the information I've given you. You maybe you wonder why I'm spending time on this. And it really isn't maybe absolutely necessary in the scope of the material we want to cover in this course to be proficient in this area of converting and working things on a pound-mole basis. But for reasons that I'll show a little later, if we want to be rigorous, or as rigorous as we can in solving distillation problems or understanding what's going on, then it is almost necessary to use pound-mole basis or mole percent basis in order to justify some of the techniques that are used. One of the reasons for that, which I'll illustrate later with a table I'll give you, is that whereas the heats of vaporization, the amount of energy required to convert a pound of water or a pound of alcohol to a vapor are considerably different. Something like 450 BTUs per pound of alcohol and about 980 BTUs per pound of water. And so the heats of vaporization, which we're concerned with when we're talking about distillation and multi-stage vaporization, is would be on a weight basis would be a function of the concentration, but useful enough when we convert to a mole basis, the heat of vaporization is almost constant. It's sufficiently constant or independent of a composition that we can assume that that we have what we call a constant molal heat of vaporization, or the heat of vaporization on a mole basis is essentially, I forgot what the figure is, about 33,000 BTUs per pound mole. And it doesn't vary more than about 1 or 2% over the whole range from 0 to 100% alcohol. So it's a simplification that enables us to solve problems that otherwise would involve complicated energy balances. Well, I think we'll let it go for that. I ask you then to try to hand in the problems 1 and 2 tomorrow morning at 8 o'clock. And in the laboratory period tomorrow, we'll have 2 or 3 things. It will include, in each section, crushing about a ton of grapes. Maybe you'll have a little help. We're going to start making some distilling wine tomorrow. And then we'll also take a little time in the laboratory to do that problem set from the gauging manual, and I'll collect all the gauging manuals I can have so there'll be enough around to work with. And perhaps a demonstration of another aspect about the laboratory.